1, 2, 3, 4, 5. Okay, sound works, so let's start our final stream about this article. And that was a big, nice journey. It taught me really a lot of things. I learned how to be more productive. Before I was just reading and thinking on my own, but I learned that it's not so hard to speak with AI assistant before the stream. So now I'm more prepared than I was before. And understood this paper to some extent, not so much. I need to think more about it, but that's the best thing I can do. It took me, I even don't know how much time. Well, I can count number of minutes for stream, and then I mean number of hours, and then multiply this by 2, and then add it. Okay, multiply by 3 and get the total amount of time how much I spent only on this article, and also add 2 hours for future writing my comments and questions which I got during the stream. Okay, so let's finally continue our discussion, and I unfortunately forgot to open it because I was reading and thinking and speaking. So we need to do like this, and that's the structure. And okay, we are here at the last part of the article, and here we need to we need to answer some general questions about Chernetsky wave and periodic lattice distortion. So it will be mostly a stream of different comments. And also I will give overview of what we have discussed throughout all this time. And let's just hope that that app will not fall, which is unfortunately probable still. Meanwhile, you can guess how many people are developing it right now. And if you say any integer positive number, then you are wrong. It's not positive and also not negative, of course. Right now, yeah, the number is less than I expected, but okay, this app still works to some extent, and that's already enough to get a lot of advantage from it. Okay, so I hope that we will it will take us no longer than 3 hours. Ideally, I would like to have 1.5 hour stream, but that approximately never happens. And okay, last time we have discussed fully ARPES results. This time, maybe I will be slightly faster because maybe I have gained some skills, but no one knows if it be faster or not. If it is faster or not, but okay. Yeah, and yes, the last part of the preface is that there is a lot of theory here in the article, and they will go through approximately 9 pages of text. So unfortunately, of course, I can't keep in mind everything what's written here, so I need to read from the beginning what was written there here, and only then I will give my comments. Okay, here we have just abstract intro, which doesn't tell us something useful. And let's also open some useful plots, which we might be referenced to. Maybe this one, because everything is about some of these plots. Okay. Okay, so here is a statement which I was thinking about several times, and it will be also in the future part of today's discussion. So I guess here we mean this, okay, maybe this is the best plot which we can look at while thinking about this statement. So this ARPES, which measures how much electrons are coming out after we shine photons. So it gives us plots of basically this plot, and then we can go along this plot. I mean, that's maybe a three-dimensional plot, so we can go through some direction along the plane and along vertical line, then we can get this plot. That's what I learned better after thinking of my posted questions. And here it's written that this charge density wave vectors can be obtained from, I guess, this plot. So here the very famous idea in scope of this article is mentioned that so there is a modulation of electronic charge, and in this article we do not see any of such plots, but there is STM measurement, and we remember it from my previous streams, and that's the essence basically of the charge density wave. So here we talk about only conventional charge density wave where everything is homogeneous, because if it's not so, then I don't know even what to say, because even about the commensurate phase there are really a lot of questions. So in this modulation there is the wave vector of modulation, and right now I'm a little bit confused because it's not like a wave, or we can actually think about it as a wave. I wasn't thinking about it ever. That's why the streams are so great, because I would never think about this way. Some questions, like I know that there is a modulation, right? That's what is well known. That's like, I mean, if we look at this one-dimensional plot, that's wave vector. What's the problem? And then they talk about two-dimensional modulation. But if we have, okay, let me show. Okay, here, that's the image of modulation, which we can see in the STM experiment. So we think about only this or this case, and other cases are beyond of everything what we can discuss, what is discussed in this paper, let's say. So here it's not really clear where is the wave vector, right? To see a modulation. Maybe there are several wave vectors. Let's just write this as a question. Okay, that's the question that I'm thinking about right now. But okay, let's suppose that that there are several wave vectors, and there is an easy way how to obtain them from experimental plots. And here it's written that we can obtain that several wave vectors from the plot of intensity. Because here that's intensity around Fermi level, so all of these dark lines are the actually lines of the Fermi level. And how it can be obtained, I have no idea. And actually I was speaking with ChatGPT for an hour approximately before doing the stream to be more prepared. And did he tell me something? No, I think no. Or maybe I didn't ask exactly this question. But the question is that there's this Fermi-surface nesting mechanism, and the idea is that if we have this increase of the susceptibility, I mean, there's the general formula for susceptibility. That's the formula. So its formula will give. I mean, it has a lot of terms, and the terms that will give the highest contribution, they are for such Q which has the little denominator, and that's the Fermi-surface nesting vectors, and that's why these Q's are also corresponding. They correspond to the Chern density wave. That's how I understand it. Maybe I'm wrong. Maybe that's a vague understanding, but that's what's written in the section. So I can just tell you what I learned from this article. There is no way for me to read all cited literature and figure out what is really meant here. So here it's written a repetition of this idea that here, if we look at this plot, then we see, oh, there are several vectors, nesting vectors. Somehow, and discussion of it goes beyond this article, but maybe I will prepare another stream about Chern density wave. So that's what we see here, and we say, oh, then most likely there will be a Chern density wave. And we will discuss later criteria, I mean, which we discussed on the second stream also, but here they will be also used for investigation. Should we expect the Chern density wave or not? And a lot of meaningful conclusions will be presented based on this criteria. Yeah, so that's what's written here, that if we look here, then we can find these vectors which will give a big contribution to susceptibility. And that's why if we go to lower temperatures, somewhere there we will have a modulation or gaps at the Fermi surface. And somehow that's that coincides with the modulation, which we haven't seen ever in scope of this article. There's a Chern density wave vector and periodic lattice distortion in commensurate phase by its definition should coincide to the Chern density wave vector. And also it's written that we can directly measure this lattice distortion. Yes, it's written here, nothing is new here. And why we can get the Chern density wave from lattice distortion? It's because we have this state binding model that we have discussed in the previous stream, during whole previous stream. And yeah, actually it's a good idea to ask ChatGPT about what exactly the tight binding parameters, but I haven't reached this question, and I'm not sure that he will answer because he needs to read cited literature and it doesn't always work well. If he had all cited literature prepared, then it would be way more sense to ask questions. That's why I actually developed this app, because here there will be all literature. So if you ask here, chat, then the answer will be way more meaningful than if he would need to search literature himself somewhere. But okay, that's about the future. Okay, here we just have a repetition what have been already observed. And yeah, so here it's written the same thing that was written in the chapter 2, that maybe I need to, yeah, that's this criterion. Criterion is already here. It has a name which we will see very soon. But right now what's important is that this approach to Chern density wave, it So the main thing is a calculation of susceptibility. Somewhere there, and I don't know where because it's nothing is written about exactly this, but somewhere there is a discussion of something which gives us this condition. Maybe there's discussion of energies, but here in this article there is already the discussion of changes of energy gain, energy loss, and that's how some analysis is done in scope of this paper. But in scope of cited paper, that's the proposed analysis which should be. And actually learned that here, I guess we need to find such Qs so that this criteria is not satisfied. Because you might ask, what is this Q? And my answer right now is that that's a special Q which just should exist. If it exists, then there is this instability. If it doesn't exist, then we don't have instability. That's how we should use this criterion. And sounds like very hard, that it's very hard, but later we will see some examples of its applicable, its usage. So what I was speaking about, that there are two these approaches of checking that we have charge density wave or we do not have charge density wave. And that's an important question because whole this theory, I still don't know what it can do useful. Really, I don't know, because okay, one thing is that it analyzes if we have a phase transition in general or not. That's what I understand, but also we have this softening of phonon modes, and it was written that they were measured, but here in this article it was not written at all. But okay, actually it's a good question. Okay, because nothing was written about it. It was just statement of the formula, and that's all. But maybe it should be used somewhere. I just haven't seen it in all of these papers. And that's what's written here, but okay, it's not about this criterion. Okay, it's about another analysis which I didn't select to this list of K formulas. Oh, but okay, we have one formula out of it. It's like the change of energy band. I still don't know why there is exactly this formula, because I haven't thought ever about it since my second stream. Maybe ChatGPT can derive it. Maybe we'll go through some of my questions and get some derivations. But in scope of this article, you should understand it beforehand, and just, oh yeah, I remember that's exactly the formula that I would write if you ask me what is the change of energy of electronic systems. If you don't know what to do, change. I mean, oh yeah, I don't know how to even explain this. Okay, it's a good question actually, which I forgot to write when I was discussing chapter 2. Okay, I learned that I don't understand well this formula, but anyway, even if I knew an answer, then that's what we said, that we don't use this formula right now. We are using, I mean, okay, we are using exactly this formula. We're not using this criterion. And also there is the positive change of lattice energy, and totally, that's how totally we use these two formulas, and we figure out if we have a positive contribution or negative contribution to the total energy. And we use this formulas at zero temperature because maybe that's easier. I mean, definitely because it's easier, but here for susceptibility, actually, yeah, I learned right now about this question that I wrote, that maybe it's not that hard to use it for finite temperature. Maybe there are some other complications which I don't see because I haven't ever used these formulas. But right now here it's like it's written like such that I think that maybe for finite temperature it shouldn't be really a big problem. But okay, we're using this criteria to figure out if we have Chernysky wave or not. Okay, here nothing is useful. They need a better approach as usual. They will try to develop microscopic mechanism. As usual, they will not succeed, but okay, that's just introduction. And that's the sentence which is the same as in the conclusion, which we have read in the first stream, I guess, somewhere, but I see it not even, okay, I see it definitely second time in the article. In another place there was nearly this sentence, but I suspect that there was another place, so I suspect that there was already two such sentences, so nothing is really useful here. So like, see, like for example, electronic structures and transport properties are so different. Yeah, they're different. So what? Yes, there are a lot of factors. We already know that there are a lot of factors. It's obvious that there are a lot of factors. And of course, as we know, the theory is not developed. And here again, nothing is useful. But if you would think that you need to think only about the band structure, then this sentence tells you that that's a bad idea. There are a lot of factors. I mean, I guess there is no person in this whole world who would really assure that you need to look only in the band structure. Because, I mean, we have lattice distortion, right? That's already something that by default is known to influence electrons, so that's a useless sentence. But okay, where is that plot? Okay, let's move it here. And that's this plot. Okay, so this is an important sentence, which I was trying to understand several times, and I discussed it with GPT. So we were given this model that we have discussed, and then we were told that actually that's a really bad model. And why is it bad model? Really, I don't remember because we were not given some clear explanation, but some abstract experiment, I mean, some abstract statements were there and some set literature were there. So the conclusion was, as far as I understand, that model is useless. But the general idea of this model, as I said, is that, except this strange normalization of frequency, that only gives us the tool for analysis, if we have a transition or not. And And that's what's written here, that we will be using still this model, but we can't use this model because that's a one-dimensional model and we have a two-dimensional material. And also he was speaking about, for example, generalization of this constant in several ways. Okay, but that's what I guess it's written here. Yeah, that's what's written here. You see, like here it's written not very clear. Physical picture. Where is the verb? In principle, correct. Physical picture is a principle correct, but that's, I mean, not a physical. I mean, that's not really what we need. We need some theory that gives us some prediction. This theory does not give us a prediction. Later it will be written that it will give us absence of Chernysty wave transfer in this material. So that's a sentence which you shouldn't understand directly. It means here the idea is that there is a discussion about why at all there is this transition, and that's the model. If you if you, I guess, work with this model, then you can get this criterion for 2 dimensions, and then you can use this criterion with some parameters that you can find from experiments and check if there is a phase transition or not. But when you do experiments, you already know that there is a phase transition. And what is T0, I unfortunately forgot, but I guess that's okay. Actually, I can just do some scrolling. And maybe that's in the table 5, and I have only table 3 and 4. So okay, right now I don't remember what is T0, but maybe the main idea here is that we will stick just to this model to do some comments or to be dissatisfied because this model just wasted our time. But instead of doing something else, Rossnagel proposes us to just squeeze as much as we can from this model, because maybe after him no one will be working with it in the future. That will be the final paper about this model, because it looks very useless. And maybe that's the biggest attempt ever done to make this model work. 1 second. Okay. Okay, I need to have a very, very short break. I will be back very soon. Okay, let's just continue. Sorry for going out. I will try not to be pausing streams as much as I can. Okay, so where have we been? Turn this. Yeah, so we will just stick to this model because that's what Rossnagel tells us. We don't know what to do else. Why do we need to do it? Well, because maybe we will try to answer this question. And to answer this question, tight-binding models may be useless because it predicts the electronic spectra based on the lattice configuration. And here we try to understand why at all there will be such a lattice configuration. And I guess that nothing will be clear, but that's our goal. So tight-binding model is not enough. The better model is not developed. We have just cited papers with some ideas about it. So that's the best approach, which possibly might work. Yeah, so that's a simplified model, but it should be still useful. Uh, and here nothing is really useful. That again, he says that even if this approach is useless, then it can give some useful intuition or clarification of factors, but nothing is useful here. Basically, what is really useful in whole this half of a page is that we are going to use this model. Okay, 5.1 qualitative explanations. Some two extreme limits will be used. And which extreme limits I don't remember on top of my head. I thought that we speak about electron-phonon interaction. And okay, before I guess, let's just read and we'll see which is meant. That's them. I'm surprised that it's not written here. I thought I wrote this. So one limit is the metallic bonding, and another one is ionic covalent bonding. Okay, so metallic is when there is long coherence length, small energy gap, and commensurate density wave, and instability of Fermi-surface. So small energy gap is what is the thing that is clear because that's what we mean by metallicity, that there is or little gap or no gap, and that's why current flows easily because electrons go to conduction band. Coherence length is long. I can only guess what it means. Maybe it means that electrons, or like orbitals of electrons, overlap, and if they overlap, it's easier for electrons to jump from one to another. So like coherent means maybe some correlation. So I mean, I don't know about this parameter. And what is the instability of Fermi-surface? That's maybe ChatGPT will answer, but I forgot to ask him about it. That's actually one of the typical point in scope of this chapter 5, that stability of Fermi-surface driven by this or that. What is the driving mechanism? And I have no idea what it means in scope of question, like what is the driving force. Maybe that like we need to think that everything is fluctuating and exactly this parameter should fluctuate for all other parameters to adjust and have a phase transition. That's just my idea, but unfortunately all of these statements will be left as just questions during the stream because it's not explained here about this idea of a driving, what drives what. But okay. Okay, and the ionic covalent bond, it's not what I understand, but I guess uh, I guess that we have like actually insulator, and there is also didn't comment about incommensurality of this, so I don't understand it, but that's just the statement here that this is the property of this bonding. And what is the physical phenomena? I don't know, I just guessed that that's the electron-phonon interaction, but maybe this is some bonding phenomenon. It's not explained here, so as you can see, it's impossible to extract some useful information. Um, um, Okay, I'm trying to understand this part of the sentence. Sum of energies of shortened length bonds is lower than energies of normal bonds. So it's written maybe that it's more energetically favorable to change bonds, one make bigger, one make smaller, and energy of this configuration will be smaller. Oof. That corresponds to a big gap or big, yeah, and big amplitude. It's actually interesting notice that if we have big, let's write it here. Okay, I'm not sure about it because I don't have really right now this intuition. Let's think. If distortion is bigger, and okay, there are two questions like. Okay, this is just the question. That's the question which I wrote. And then better not to try to answer because I can be just 100% wrong with all my guesses because I wasn't working with formulas. And if you are not working with formulas, then you can be just wrong. So, but there is still this connection between amplitude of lattice distortion and the gap. And it's a good idea to clarify this connection here. It's just mentioned that if amplitude is large, then gap is large. So better for me not to try connect it because right now I might prove that, I mean, give some arguments why it's not so. And okay, so okay, here GPT helped me somehow to understand it. So these are the two mechanisms of bonds. And tight binding model has some parameters which is calculated through overlap of integrals of, through integrals that correspond to overlap of electronic orbitals. And basically in tight binding model, one or another limit can be implemented. That's how I understand this sentence. I'm not expert in chemical bonds, so, and of course I haven't opened ever the site literature, but if you want to understand it better, the only way is to see site literature or to speak with AI, but if there is no better information, then there is no way to understand it better. And here it's written that, okay, we have these two extrema, metallic and ionic covalent, which is like insulating. And if lower temperature, then these bonds change and we go from metallic state to insulating state. That's what we know. That's just paraphrasing it in this picture of bondings. And maybe people who work with state binding model, who understand this model, they will see that that's the very true and deep statement. I mean, the very true statement. But right now it looks like a paraphrasing. And I mean that nothing is really very useful here because we are not given formulas to work with state binding models, unfortunately. So that's just a comment about what is assumed there in that formalism that is cited. Okay. Okay, so that's the sentence which made me very confused when I was reading it, and right now I also don't understand it. So if we have these how to say it, defects, how do we call it, alloy with some impurity. Yeah, I meant impurity. So if we have an impurity, then Chern density wave vector depends like this for the concentration of impurity. But so it's actually interesting that we can maybe it's actually I don't know, let me remind myself. So here it's about only this material. So it's not about this material. We will not go to these materials and these limits. But it's actually interesting to know what would be if we add like tantalum to selenite. Then would we go from this picture to this picture? It's really a good research. Actually, let me write it. It's a good question. That's a very good question, I think. Here we are not given this good question. We are given a change of this material to another one, and that's very strange. I really can't explain it. I can't comment it somehow. That this vector depends like this. So at the limit of only titanium sulfide, we don't have a Chern density wave state at all. But if we have a tantalum titanium sulfide, then we have this dependence. It's also not clear what's written size of Fermi-surface, because X, it's actually the number of impurity, it's not the size of Fermi-surface. So that's a clear sentence, but the statement which is meant here, it's very surprising. I have no idea why is it so. But maybe, okay, maybe I forgot, and here there will be some explanation of what happens and why. Okay, I'm just a little bit changing my settings. Okay, but let's just focus. Let's not be unfocused. That's the focus structure tool. And we need to be focused. So, okay, I'm trying to read right now the question here. The sentence I mean here. Okay, so there is a shrinking nesting vector across M elliptical Fermi surface, figure 11. Okay, I need to scroll for it, but okay, let's try to open it like this, and then like this. So that's the assumed figure, and there is this nesting vector. So if we decrease the concentration of tantalum atoms and increase concentration of titanium atoms, then we will get shrinking of it. And that's very expected because here we're already given a formula for the wave vectors. If it diminishes, then Fermi surface, I mean, of this type should be decreased. Yeah, and that's why it's written that this Fermi surface nesting, that we need to look at the Fermi surface, and only exactly from these electrons there is this contribution to susceptibility. So exactly this is the driving force. That's the main reason of this transition. That's what's written here. That's the argument of this Fermi surface nesting. And what is the contradiction from some experiments that cited? I don't know. It's written that this material can be regarded as mixed valence compound. And yes, so of course, okay, suppose that's the mixed valence compound, but what's the problem? And it's written that, so it's not clear which experiment, which exactly experiments and how they suggest that it's a mixed valence compound, but because of them and because of this property, we should think that there is local bonding property, and if there is this local bonding property, then it somehow should contradict this idea of the Fermi surface. So maybe Fermi surface is about the conduction electrons and bonding is about the localized electrons, and here it's meant that localized are more important, and all this picture of Fermi surface nesting is not usable, but we know formulas to which we assume here, and here nothing is connected to that formulas. So I don't really know what is really meant here. Yeah, so here there is a little clarification of this idea, which I already explained, that there is state-bound model. It has some parameters. They are calculated through overlaps, and if atoms change, like at periodic atomic lattice is changed, then the Hopper integrals are changed, then a lot of things can happen, like splitting of a band or increasing or decreasing energy. And all of them were calculated. Actually, it's not so hard to just do some little scrolling. And that's actually what is meant here. So all of these bands, they just appear from the local atomic bondings. That's what is referenced to, this statement is referenced to. And there's a little discussion about the first material, tantalum disulfide. What important can we get? Actually nothing. Approximately one idea can be used, or another idea, but we are just going to the second material. So here maybe we have consistency of two vectors. I'm just confused a little bit because here for this material nothing was written about it, but here it's written that they are consistent. So I guess for the first material it wasn't the case. What is really meant here? I need to open figure 12. So that's the figure that they assume. So I guess if you calculate susceptibility along the vector along this direction, then it will be big, and that's why this vector is the vector of charge density wave. And if there are several vectors in charge density wave, then I don't know, because I haven't understood this feature yet. And again, when we were discussing this material, there was discussion of this special part of this diagram, and Fermi-surface is near Brillouin zone, and I guess it means that if we have the little Brillouin zone, then the gap will be at these points, and if we have a Fermi level here close to it, then gap will be around the Fermi level. That's why it disappears, approximately, and that's an important sign of this commensurity. This is the theory we are given here about description of this. And that reminds us the perilous instability. However, okay, that's, yeah, the similar pictures as I have discussed is for one-dimensional model. It's really good to have in mind at least some formula for this explanation. But since this article is not showing us how to use formulas, I don't know how to plug this effect into formula. Yeah, and that's what I explained here. And okay, we need to remember this points. To remember the points, we need to just scroll. See how fast I can scroll. So here are the points, and the gap, yeah, here opens. That's what we saw in the previous image. So that's one explanation about this material. Now we are going to another explanation when we look at the lattice distortion. And okay, it's not that hard to open this picture. That's the lattice distortion. And that's what this little statement which I don't understand. Here it's written 9 atom, but I calculated it and it was not really 9. 1, 2, 3, 4, 5, 6, 7. 7 atoms. Okay, what's meant here? I don't know. Maybe again it's meant that we need to use state binding models, put the atom distortion there and get some new features. But here maybe the binding model also can be assumed. Fermi-surface is changed. Yeah, it doesn't look like it's purely another discussion. Purely another approach, I mean. There are two submanifolds, and I can only guess what is meant here. Yes, I can open that plot from the previous stream of the binding calculations, but it's I don't really want. Anyway, we will not understand what exactly is meant here. Maybe by submanifold, we mean the collection of bands, and some of them were more in the center, some of them more in the top, and there are these bands. And yes, of course, as we know that the phase transition occurs, then distortion structure is energetically more favorable. Maybe it's meant that if we do this calculation for new parameters, then we will find that there is lower energy of this distortion configuration. So to conclude, nothing is really important about this material is written here. Okay. Now we have the bigger discussion. Like, I mean, I'm trying to summarize here. Yes, it's written that the gap disappears at the Fermi level. And also, if we do the binding model, then we can also get a good explanation. Are these two different explanations, or you can just have different version of retelling what happens in scope of the same model? That's what I don't know, because nothing is written about both models in terms of formulas. But that's all what's written here. Now the third material. It's written that something will be different. Something will be different because, as was announced before, this material has some excitonic insulating properties. I mean, it can be also explained by this model, and that's why today there will be a discussion about it here in this paragraph. And soon we will finish 5.1. Okay, I maybe forgot to read this sentence because usually I comment all meaningful sentences, and here I forgot to read it. Okay, main conclusion that Fermi-surface nesting can be ruled out because we will not find these vectors. It's very hard to discuss it without pauses, unfortunately, because you see, like, band structure topology suggested of the observed wave vector. So if we look at the bands, then we know, actually I was trying to learn how it is connected to the Chernetsky wave vector. ChatGPT tried to tell me the answer, but I still don't understand it, and it's better not to focus on this important question because I don't think that I can answer it even with AI in 10 minutes or 20 minutes. So just it's a very good question that, yes, okay, we have bands, but what can we say about this Chernetsky wave vector? Because here, all of the ARPES plots, they do not tell us anything about Chernetsky wave vector. Maybe if we know that there is Chernetsky wave gap somewhere here, then we can say that exactly this point and this point, so the Chernetsky wave vector looks to the M direction. But no, really, I better not to guess. So what is meant by this vector? I don't know how to explain it from this plot. And I have explained in the beginning of the stream what I assume by this Chernetsky wave vector. But somehow these great experts, they look at this plot and get that and see how see something about Chernetsky wave vector. Okay. But what is it? What do we know about Chernetsky wave vector? It's not what's written here, so maybe we know some position of it. Like maybe we know the direction of it. So maybe we need to connect minimum and maximum of two bands, and to this direction there will be this wave vector. That's how I guess it's meant here, what I guess it's meant here. But I need to see formulas, of course, to be assured. And it's written that that interaction of the band is the K mechanism for this material. So something very different here comparing to the previous ones, because this approach doesn't work. The band local chemical bonding approach is not discussed yet, but this new approach of interaction of bands is presented in the third material. So another purely different model should be used for explanation of similar phenomena. And also we see that, I mean, from experiments it's obvious, but from theory it's also can be shown somehow that the state is stable because, of course, energy is lower. And that's obvious thing that we have discussed, but no, what is not obvious as to how to derive it. And it's written here that somehow people proved it. I guess so. Now there is this question about, is it a phononic or excitonic effect? Maybe it's meant that, okay, I don't know what is meant really, but like if we do phonons, we have several bands and electrons are in the influence of phonons. If we do excitonic, so we need to take two bands like electron and hole and then couple them. So maybe that's what it means, that do we need interaction of electrons and phonons or no to explain this change of the state. And then if we already have a change of the state, if we're sure, then we just change the lattice distortion according to electronic states. That would be for the excitonic case, and for phonomic case, that's a purely different mechanism. So we need to couple electrons and phonons, and only then we have the change. That's what I think is meant here. Oh. I'm already reading this sentence third time to understand. So one electron total energy change is connected. Changing. Okay, so that's useless sentence. I mean, we know it, we have discussed it already. Yeah, so I didn't put the right comment in the beginning, which I should have done, that nothing is useful here. Yes, we know that by coupling of phonons, we mean that parallax model that we have discussed already. Yes, and again, we have this bond pictures, and in scope of this picture, like I'm not given any introduction to this theory, but there is another explanation how to explain lowering of energy. So there is a strengthening of the bond. And it's not clear if these are similar effects or different effects, actually, because anyway, lattice is changed. It's maybe the question about what to take into account first. Observed distortion parts. Yeah, so okay, let's just forget it and read this sentence. Yeah, so again, distortion patterns change the bonds, and bonds basically are in the Taliban model that gives us the change of energy, and the gap appears because of this. Yeah, okay, and here, as I announced, it's written about the excitonic insulating scenario. And the gap can appear because of this scenario. So just a link to the previous discussion, chapter 2, but reminder, nothing is clear there, so you need to read cited papers about this model. But here they just point out that interaction of bands is the key in scope of this approach. And that's why if it's a K1, then we can use different adjectives, for example, electronic. Yes, nothing is important here. And that's the conclusion which we already imagined before, that both of them can explain this transition. And here, that's the sentence which is not very clear, but that's my reminder to myself that it's meant here that maybe the so there are these two approaches, and they guess that the coupling to phonons in this strange model is more favorable than bonding. And why? It's not written why, it just seems more natural, but again, nothing is working fully. And this model, which is more favorable out of two, is not producing some gap. Some plot, of course, is assumed here, the binary results and the ARPES, so that's the ARPES. And I'm too lazy to scroll for the tight binding results. But maybe some gap. That's maybe that discussion that if they don't increase the 2 times the distortion of the lattice, then they don't have the gap. I mean, I think that's the fact that is referenced here. And maybe that's why there should be excitonic model also here. So one thing is that atomic distortion, second thing is excitonic contribution. Together they give the gap that is obtained in experiments. That's, I guess, the idea that's present here. Okay, summary should be really quick. Okay, this sentence just says that the ideas that we have discussed are approximately useful. Yes, and that's important, like comment that all of this discussion deals with already known results, so we do not predict anything new. We just try to work the model that will explain the obtained results. That's all what is done here. So if you want to predict something new, then you will have a big problem, because here, even for these materials, it's not done, but a lot of people worldwide are studying them. That's what's written here. And here it's a little bit strange statement, because it's written that cannot predict that this transition should occur, but I was saying before that exactly this is what is predicted. And here is written that it does not predict. So if it does not predict, then what at all is the value of this? Yeah, like maybe that's just a wrong formulation. That's what I understand. Because no, like local chemical bondings are giving change of spectrum, but Fermi-surface nesting is the mechanism that is right in scope of the, how Rossnagel calls it, mean field weak coupling theory for 2 dimensions. So that's, I think, just the wrong formulation of this sentence. What's written here? So it's interesting to see such adjectives here. So Fermi-surface can be seen as one electron contribution. Local bond contributions can be seen at exchange correlation energies. It's nice adjectives which are not telling us anything useful, but in these papers there will be a bigger discussion of all of this. And of course, no one was trying to separate Okay, maybe here it's meant that they're separate contributions, but Rossnagel then writes that it's not reasonable to separate them. But I guess that's what happens throughout this paper. They're just separated because Rossnagel discusses the one contribution and another, but since no formula is given, then we can just guess what is really meant. Now we will move to more quantitative models, but I don't know what is meant by less specific, because less specific. Okay, I understood. So we deal with specific models like particular materials, and right now we will go to the general models, I guess. What is more quantitative? I guess that's more general. And okay, here we're just given some ideas and some statements about something working or not working. Okay, let's just check how much pages are we left. 1, 2, 3. Okay, we have a lot of pages, but I really want to finish today this discussion and not to have 8th part. Okay, now we will discuss the existence, and everything is about this criteria. So before we discussed, I guess, the factors that give us this transition. Let's change qualitative explanation. So I mean, it's not written like this exactly, but it's written that which factors are in general assumed by these formulas, which we haven't seen ever, because to see them we need to look at cited papers, and no one, I mean, it's very uncomfortable to look at cited papers. Okay. Yeah, okay, as I announced that this energy gain condition is I was also discussing in the beginning of the stream. The contribution of electrons and lattice total should be less than 0. That's why it should be energetically favorable. And maybe this criterion is consequences of this formula. I didn't check it, but here in this paper, Rossnagel calculates this by himself and also uses this criteria by himself. I mean, without connecting them together. That's why I'm not assured, but it could be like a particular approach to this equation also. But okay, that's the criterion which was already discussed before. We don't know why it is so, but there is a paper where you can learn why it is so. Yeah. Yeah, so that's these two approaches about the condition of stability. And yes, they will do both. And that's the first approach, which will be used Chan-Heine criteria. So we need to have these terms. I forgot which correspond to which. Something is electron-coulomb interaction, something is exchange interaction, maybe vice versa. I wasn't working with this theory, but it's written here that you can use some perturbation theory with some simplifications. With the simplifications, you get one of the terms in this equation. And if you use this approach, then you need to know bands and calculate over bands. And then you neglect electron interactions, because maybe it's too hard to calculate them. I don't know how to calculate them actually. And yes, to use this criterion, we need to plug in some parameters which we need to know. That's what's written here, of course. And yeah, and to do this, we need some parameters that will be shown table 5. That's the table 5. Later I will go through it shortly. Right now, it's written that this table is created for using this criterion. It was created by previous experiments and from Rossnagel's experiments in this article. Yeah. Okay, so there are comments about how these parameters were obtained. So yeah, so I don't understand it. That's why it's written here. But somehow I can get stability from measured band structures. Maybe because of this formula. So we know how they are changed. Maybe we know this like local Coulomb interaction because of geometry, which we assume static. And I mean, if we have thermal fluctuations, then I don't know what to do. But if atom stays on their place, then like we know the positions of atoms, so we can calculate this interaction energy. And that's how I guess we can obtain this susceptibility. And another thing is that we can obtain the the coupling constant from critical temperature. Fortunately, I forgot what about this omega Q0. Maybe Q0 we also get from another place, and then we know it. I forgot about the Q0, but actually we can remind ourselves in this table. No, there is nothing in Q0. But okay, we don't care because in this transition temperature there is already this combination that we're interested in, so we don't need to extract this exactly omega Q0. But I have already thought today about this question before the stream. Which Q0 should be here, and maybe it's assumed here that there is just exactly one particular Q0 that is meant. Because for you, there is the highest divergence in susceptibility. That's how I interpret it, but here it becomes even more confusing because like if we look at the Fermi-surface, there could be a lot of nested vectors. And here we have just one Q0, so it's not clear what is the one Q0. But okay, suppose we just work with materials which have only one Q0. Here, the answer is written on the question why we get the electron coupling term from superconductive phase temperature of transition to superconductivity. And right now you can feel that the quality of the streams becomes higher because it already can give you some meaningful answer. So the idea is that that's first of all a bad estimation, and maybe that's fully wrong. But the idea which was here is that if we go to another region of temperature, another region of pressure, then there will be a superconducting state, and we can use a formula for critical temperature as a function of coupling constant. And of course, and also the Coulomb interaction will be included because maybe people just know how to do it, so it's easier to include it. That's the Macmillan's formula for superconducting transition temperature. And they measure this temperature, and then that's how they get this electron-phonon coupling. Is it the standard way or no? I am not sure. But we have a citation for this approach to check it. Yeah, and that's exactly what is written here, which I, by the way, wasn't reading for several days because I was preparing about exactly this part just some days before the stream, not right before the stream. So that's the same thing here. It's written here, but by the author of the paper. that indeed they need to go to another region of conditions, like put the pressure. They also write that it's a hydrostatic pressure, and it's something that I don't know because I thought it's just like a atmospheric pressure. But this is a rather detail. And also it can be because of impurities, because as it was written in some other articles, impurity gives the same, similar, or the same effect as adding pressure. It wasn't clear if it's the same effect or not, but definitely it's the similar effect. And in both cases, superconductivity can be induced via suppression of this phase. So what I guess it means that we go to the metallic phase, and also there will be no here it's written that there will be no coexistence. In the previous paper somewhere there, I remember this plot, so it was written something that there is a region of coexistence, but all of these are just phrases. There were no exactly measurements and no formulas about this region. It was just comment like this. But here in scope of this theory, there is or density wave or superconductivity. And if we go to region of superconductivity, then there is suppression of the first phase. And yeah, here it's written that if we see the, it's actually a good question, like what about state? That's right here. Okay, that's the question about it, what I'm reading right now. Novel superconducting states are characteristic of, so here it's written that in superconducting state nothing is modulated, no charge density wave. That's the idea of this sentence. So free from theory and experiment, it's bad that they don't distinguish it from theory or experiments, but okay, that's one table out of these two sources, types of sources. I don't know how to obtain some parameters, for example, the susceptibility, which is here like inverse susceptibility. And okay, yes, band versus lattice energy, just selected rows of the table are discussed here. And yeah, I don't know how it is obtained. It's an activity for at least a week to check some references. And to understand really how something here was obtained, I guess the majority of them is from experiments, or also it's a combination of table 4. I mean, the data in table 4 is used to obtain some data here, but I wasn't working with this table. We are just given some useful parameters for basically this condition to check if there is instability or not, but we already know that there is some instability because, for example, like if we measure superconducting temperature, we need to go to higher pressures, and to go to higher pressures, we need to know that at low pressures actually there is no superconductivity, because you will see that there is this charge density wave. But okay, this is like complicated results. There is some meaning of them which is not clear here, but there are luckily some citations to explain everything. Yeah, here actually it's written. Yeah, unfortunately I was confused. So okay, here it's also written something which is very similar to what's written here, and I have already discussed it. And there was actually little discussion about this parameter of electron-phonon coupling term. It's not clear what is really meant by this like parameter of coupling. It could be or j squared or lambda, or I remember that there was some effective term which is a division of two terms which was called like electron-phonon coupling. But okay, here it's just mentioning of this obtaining term from superconductive temperature. And I think we will soon finish because I want to do it faster. Nothing is really available here, just comments. But I mean, of course, that's a very valuable table which professionals will use a lot for their estimations. But for me, it's hard to see how to implement some data from this table to some criterion, and we have only this criterion to work with. Okay, let's just count pages, and then I will do a very short break, and then I will continue. 1 page is left, 2 pages, 3 pages, 5 pages. Okay, a little bit more than 5 pages. Okay, that's fine, and I'll continue in a minute or maybe less. Okay, let's continue. So we want to use this criterion for stability of this state, I mean for prediction of charge density wave state in general, and we are continuing discussion of these parameters, and they're related to superconductivity. For example, we can get this coupling from the transition temperature, and let's see what's written next. That's what I thought today, but I wasn't reading this part. I was discussing with ChatGPT this. So there is, it's unclear statement. So here it's written that superconductivity is averaged over all wave vectors. And I don't really know what is meant. Maybe it's meant that there is the gap equation where we sum over region near Fermi-surface, and like that's how we, I mean, because the theory of superconductivity that I'm familiar with, it uses a constant G. And here it's meant that actually G is not a constant. So there in superconductivity, it's assumed that we do the averaging. That's what is meant here. and Rossnagel sees it as drawback, but I haven't worked with superconductivity with like Q-dependent constant yet. Yeah, maybe it will be indeed like just in the gap equation, and we will just do the averaging, and after averaging we get this constant out. But I haven't seen just such articles which work with this Q-dependent coupling and superconductivity. I'm sure that that's already researched, but I wasn't just working with this. Yes, and anyway, it's not important. That's what's written here. We can just use this TC and say that that's a good way to get the electron-phonon coupling, and then put all the inputs to this criterion. Okay, there is also this explicit formula, so the comment that I was giving writing myself before, it's actually expanded here. So that's the formula, that's the coupling, that's the transition temperature, so we need to know the bias temperature. So how to know the bias temperature, I don't know, but that's a question to people who are doing experiments. Maybe later we'll also learn this, but okay, we need to know this, and that we can also obtain from some experiment. And the mu is something that I don't know. Maybe it originates from some theory, but I can't comment it. And this lambda is connected to the term that we need. And we need also to know the density of states at Fermi-surface, and maybe some measurements. Yeah, okay, they will be discussed in the next sentence. So I have literally no idea how to determine it from band structures, and I still haven't read a textbook of condensed matter which will explain to me how does it happen that we have a spectral weight on a band. Somehow it happens, but I haven't reached this revision of this theory. But okay, it's not also clear how to get the N0. We have just comments that may be from specific heat measurements or band structures, but that's a hard question. I don't know how to do it, but somehow this density of state is obtained. That's like more experimental side, when you know how to obtain parameters and just know formulas. And I was working more with theoretical sides when we try to derive formulas, and we don't know much about how to obtain the parameters. Yeah, and again, we're referenced again to the condition that we want to find parameters for. So we need two later parameters. Okay, so nothing is explained here, but we're given just same values. So that's the very bad explanation. Of course, there is no reason, no way to understand it, but okay, we just have cited paper about these parameters. Now we are starting next paragraph. Yeah, okay, so then we put them to the criterion, which is already mentioned here and in the whole beginning of this section, maybe paragraph in scope of this section. And the important statement is that this criteria is not satisfied for all of the systems. Soon we will see that for one it's not satisfied. Okay, what is a tendency towards? Yeah, okay, so there is another question that here, like if we look at the table 5, we get psi 0 over 0, but we need psi 0 over q, so we need to get this psi 0 over 0. Okay, maybe we don't need to get it. We have already this psi 0 over q0 and just use this part of a table. That's the old comment, which I should just rewrite. Yeah, and I mean, that's just a little comment that why do we need to compare it with 1, but it's not really important when it, yeah, just the way how we present, how the data is presented, so maybe that's a not important question. And second question, yeah, basically that's the Q0, so it's not really a question, we need to erase it. And here it's written the tendency towards formation is weakest, strongest, and intermediate in all three materials. But I'm a little bit confused because I remember that later it will be written that for tantalum disulfide, this criterion does not predict the transition. So let's just remember what's written here, and then we'll return to this. And is there in table 5 there is no such full equation to compare it with 0, fortunately. By C table 5, I guess that C some values like 1 over Q0, so that's the right hand side, it's clearly there. This thing is also maybe there, so we can easily use this criterion. Okay, maybe they analyze it step by step from maybe left hand side, from maybe maybe it's from this equation, like, and from right hand side of this inequality. That's why we do something. That's why we say that there is this tendency because of just the right hand side. Now he thinks about left hand side. Of course, he writes it too wide. He could have written it more compact. And we already know that we need the small value of this, yeah, of 1 over xi 0. Now it's written that to get this little q0, we need to have n over 0. Yeah, okay, the link is missing. I need to read this formula. We have explicit expression of xi 0 over n0, and that's what's written here. And n0 is luckily obtained. There is the comment about n0, that's the comment. So I don't understand how, but we already have this data, and that could be a good thing for estimations. And high to low transition temperatures are like this, which is okay. Now I will know it, but before I didn't notice it. I thought that for tantalum diselenide transition temperature is higher than for titanium diselenide. But okay. So, but okay, N0, N of 0, it's changed like this. I mean, from high to low for these materials. But it doesn't mean that it should be, its transition temperature should be like this. Right, we have just a criterion, so it does not mean that there will be higher or lower transition temperature. So this abstract comparison, which are not really meaningful. Okay, we have calculated several things in the section 4. Tate Biden model was a good model and did approximately good predictions. And that's important to discuss and to remind, because we will work with delta E band, and that's a parameter can be which is obtained from the Tate Biden calculation. And yes, let's look once at it. That's this column, that's this row, I mean, and all of these values are here with experimental error. So of course I can't comment you much, but this is the data that is presented. So a lot of people were sitting and thinking about this change of energy, and these results appeared. Where is it? I think it was somewhere. Yeah, it was somewhere here. Yeah, we're discussing this change of energy band. Yes. Squared. Okay, I don't know what is normalization of results, but maybe it's meant that when the results are modified to work with them in the proper way. I don't know what it means here, normalization. So proper way is some proper way. Then we can find that I guess little g parameter is large for this and smaller for these materials. And what is meant here, it's not clear. We're not given the value of this little g parameter. But out of some other results, we can get this parameter. I guess it should be obtained only from this result. We also need to know omega q0, which is another thing that is not commented, but maybe here it will be written. So somehow at this point we are coming to conclusion about this little g squared. Direction increase analytic. Yeah, okay, now we discuss the lattice energy. So we know this formula from the discussion of the first stream, and it's also not clear what is the Q here, but I guess it is meant just one Q. Later I'll ask AI assistant, but for now, that's thing that we accept, and we need to find this omega Q0 to put into this formula for lattice, change of energy of lattice. And here we see already a statement for which I wrote already a question, that why do we use a normalized phonon frequency if actually we need to use a normalized one? Nothing is written about it, so maybe that's the weak point of this whole discussion. Maybe it's really a good question. Maybe if I knew better this theory, I would improve it, try to improve it myself by taking into account already known normalized frequency. But I'm not that strong yet in this theory. Okay, maybe the explanation is already here, that we are anyway trying to get the biggest lattice energy possible, and for it we need to have the biggest frequency, the biggest displacement. So if we take normalized frequency, then it will be way lower, and here the goal is to get the upper band limit. That's what's written here. Yeah, that's what's written here. That's the lattice energy, and that's the little paragraph of discussion of it. And here is the statement that I was referring to before, that for this material, potassium disulfide, what? Not for tantalum disulfide. So this instability does not occur for this material. That's really, really strange, because before, I forgot already at which point something was. Yeah, so here it's written tendency toward formation is strongest, intermediate in this material, and later using the same criteria we are coming to conclusion that there is no phase transition at all. So that's the bad formulation of the sentence here, because it's not clear what is the tendency of towards this formation. I will just mark it as unclear one, because here we see the clear conclusion that this model, it's unclear how to use it, but even if you use it very properly, you will see no phase transition. And based on how these theories are presented, it's very hard and very uncomfortable to figure out how to fix this theory to get the phase transition. So it's also interesting direction for research is to understand if some of the questions here were answered or no. But that's one of the questions that I already wrote about this article. Okay, now we have some force constants, which suddenly jump into the game. And I don't know what are the force constants, nothing is explained here. I just can tell you what happens here. That's maybe gap at zero temperature. That's what maybe we need to see here. Yes, I don't know. And actually here, this parameter was, I think, referenced to as the electron-phonon coupling constant, as far as I remember, somewhere in the article. I'm too lazy, and it will be a bad idea to try to search it, but that's what I remember. And here it's written that's like universal value, maybe out of 3 parameters. I mean 3 materials. And that's how we get this value. Okay, I don't really see these intermediate steps, but the idea is we need to calculate the lattice energy, and for it we need some parameters, and we are getting like maximum displacement. And that's the result of this parameter. Maybe for all the compounds, yeah, okay, so that's just the conclusion. So maybe there should be u squared here, maybe that's the typo. No, there shouldn't be u squared because of the dimensions, so that's right. Yeah, and that's the answer about these dimensions. I already see the answer to this question. Okay, let's just continue reading. And right now, that's the sentence which is not very clear. Before it was written that we don't see a phase transition fault in disulfide, but now we determine some force constants, and I have no idea what happens, but it's written that in this case, in some case, nothing is explained here, this instability can be attained. It's not obtained. I guess it's meant instability can be present in this material. But what happens here, that's absolutely unclear. There is no way to understand it because of just bad formulation of sentences. And the sentence which we again should forget, that something is consistent with experimental data, but we don't see, it's not written what exactly is meant here, and some inconsistency were highlighted before, but again without explanation, so that's a rather useless sentence which you should forget. And okay, maybe I will change this question to a comment. It was written before that all of these ideas are rather not precise. For example, not calculation, but estimation of electron-phonon coupling through transition temperature, for example. That's already a big strange idea. And all of it is made based on crude models, yes, and approximations. Even experiments have big approximation, like that approximation of gaps, which we have seen in some of the previous streams. And I don't know which are generally important factors were estimated, because we saw a lot of comments about physics here, but these were just like abstract comments. They're not connected to formulas in scope of this article, but there are of course cited articles, so maybe later we'll understand the general important factors. Right now, when I don't see formulas, I can't say if there is a meaning of them or not. Okay, here, as I wrote, the idea is that something important can be predicted here using theory before. Yeah, actual order of the strength can be observed. Yeah, can be seen in the criteria or in the energy approaches. So yes, like that's what we know, because these ideas were about just checking how favorable it is for system to have a phase transition, and of course it was not used for calculation of the gap or the distortion amplitude. Okay. And again, we see again the okay, it's not, and that's not, I mean, that's one paragraph, but it's not united with one idea. So here it's written that again about the tendency, but it's not clear what is the tendency. So it's again the sentence which should be better forgotten, because there is no way to understand what is really meant by this tendency. And again, as I was saying before, maybe that's the third, but I don't know out of how many times when Rossnagel writes about the detailed balance and several factors. And yes, that's what we know throughout this article, that's just repetition of the same sentence. Okay, we did 5.2. What is the summary of 5.2? Basically, that's the data that we have, and we have this criterion to which we can put some data from the table. And also we have some cited papers which give extra comments about this data. But maybe citations, there are not so many citations here. Maybe in this one, but some statements are such unclear that I don't think that it's worth of thinking about it. There's no way to understand what's meant here. Like, for example, here, harmonic stability is attributed, but like why in which case? Like, what do we take into account? That's just his abstract discussion of everything that he is thinking about and repetition of some statements that already given before. So now finally the last one, transition temperatures. So let's check how big is this one. And that's finally nearly 2 pages, and I'm really happy that I have nearly finished this article. Oh, that's a big challenge. Okay. And okay, we have already discussed that this is not a working approach, but here maybe the main idea is that the key problem of this approach is the weak coupling limit, and we need a strong coupling. That's what's meant here. And everything here will be around just one plot that you have just seen when I was scrolling, so I remember what happens here. So the strong coupling model will be discussed. It's cited, but nothing is known about it except this citation in scope of this article. It's not discussed, but Macmillan was working and thinking about strong coupling model for this material, and he gave some useful formulas for us. Okay, so I don't see connection between this sentence and this sentence, but the idea is that we just are going to discuss something about strong coupling model and connect with transition temperatures, and for strong coupling model we will use this theory from this cited paper. Okay, so here that's the transition temperature for one-dimensional model, and with weak coupling, the BCS model, and that's the cited formula for this unknown for me theory with strong coupling. And we will use already known for us parameters from tables that we already know, so it's a fun exercise to calculate something here. Maybe it's about just T0, transition temperature. And okay, here we have this clarification of this big constant C. During the one of the previous streams when I was discussing this, I didn't know what is it, but here that's the formula for it, so now I know. And that's T0, but we need to know this big omega, for example. Are we given this big omega? Let's check. 10 to 10. No, 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 no. Oh no, scrolling. Okay, I don't need to scroll. I can do it in a clever way. Let's go back to the theory that we need to work with. I can just click here, and that's the formula for, I mean, not formula, but just a table for, and that's table 5. So maybe we need to be clever people and use this lattice constant and use the geometry of unit cell to figure out what is the big omega, because maybe that's the volume of unit cell, but right now I'm not able to produce it. And I also don't understand these comments about about this. So here we have psi 0 and it's equal to lambda 0, so we need to know this distortion, which is it a constant or not? Why should it be a constant? Actually, it's okay. Yeah, as function of temperature. It was obvious in the parallels model, but here if we decrease temperature, like one can expect that actually lattice will change. I mean, lattice indeed changes. There are a lot of phases, but the question is that maybe even in scope of one phase, okay, maybe in commensurate phase it can't be changed because of some ideas of just filling all the positions of electrons, but okay, I'll think a little bit about it later. So I don't really have intuition about this equation. This equation is absolutely impossible to derive without looking at this paper. And now we are proposed to see figure 14, which we are going to see very soon. So the figure 14 will show us comparison the measured temperature against lattice distortion, relative lattice distortion. So why exactly them are here, I don't know. That was the question that is already written somewhere there. But that's not the only one plot, which I don't understand why it has a form that it has. Yes, on this side, this linear relation. But I don't agree that it's important because we have checked it only for 3 materials. For other materials, it will be not there. And he already wrote that the mechanism for the third material is proposed to be purely different comparing to the first 2 materials. So there is no sense for us to expect that it's a universal relationship. And here there is a sentence which made me always think, I mean, not only this one, I think there were several similar sentences. For example, in chapter 2, let's check what is table of contents to. Yeah, in chapter 2. So actually, it's interesting that after discussing chapter 3, I don't really remember. So there was a table 4, but it was everything just about table 4. Nothing is really like something that I will remember from chapter 3, just abstract comments. And chapter 2 is the most important from theoretical point of view. So there already it was written that weak coupling theory is a bad one. And here we're told this again, but before it was written that exactly this weak coupling theory, exactly this one is used for analysis. So that's how this paper is created. First of all, there is usage of this theory. Second of all, it's written that that's a bad theory. Is it a good idea to write such papers? I don't know, but 1,000 people have cited this paper. But maybe actually that's Macmillan's work, I guess. So he was, I guess, saying that weak coupling theory is very bad, but Rossnagel says that it's not so bad. It's bad, but maybe a little bit less. And soon we will see this figure 14, which I consider not so useful, but okay, we will shortly come to it. Okay, so here that's about this plot actually. So okay, let's just look at this plot and then read some comments here. So idea is that I don't like this idea. That looks like a very bad idea, but it's that we can use the same model for all of the three materials, but change lattice distortion, and with change lattice distortion, we can check what is the transition temperature. It sounds like a really bad approach, because if we input all knowledge about the material, then we already should have the lattice distortion. We can't vary lattice distortion. And because it's meant that it's a constant distortion which is stable, and this stable distortion will have the stable Chernysty wave state. So I think that's just a really bad approach, which we shouldn't think much about. But somehow, if we fix some parameters and plug different lattice distortion, then for all three theories we have this linear dependence. The question is that what is the correct theory? And it's not clear what is the strong coupling theory. Maybe something in between is the best option, but we don't know what is in between because we don't see any particular parameter of really strong coupling. But okay, some parameter was used for the strong coupling, and the result was like this. Here, the transition temperature here and here, because we know that lattice distortion is this, and this for all three materials. And in this way, that's a nice plot for comparing lattice distortions. The biggest here, the second, and the third one for like in terms of magnitude. And note that there is this logarithmic scale on the x-axis. But this scale is something that I have no idea how to understand. The vertical line is fully broken. I haven't asked any AI assistant right now to explain this, but okay. Let's just imagine that there are no this no transition temperature should be 100, 200. Maybe I don't know, like, okay, we need to, yeah, like you see, like it makes no sense, but if you think in a clear way, if you know the answer, then you can interpret it in the right way, but what is written here just doesn't make sense. Okay, so what we are given? Three models that predict from some definitely like an incorrect approach transition temperatures as a linear function. And now we are comparing what we know with the prediction. We say like, oh, maybe it's here or maybe it's here. But I don't think that there are like such weak coupling and strong coupling. There are a lot of intermediate lines. So, and also we don't need to have such linear dependence. It's very unphysical to vary lattice distortion, because we speak about static lattice distortion, which is stabilized in this material. So it's impossible to get some point somewhere here, right? Or no, maybe like something is assumed there. Like, I mean, for different materials, there are different many parameters, and on this plot will vary just lattice distortion. But if we fix all the parameters, then only one point in the whole plot will be present. If we change the material, it means that we change other parameters, so it's a different theory. So that's a really, really bad approach. I don't think that there is any sense of this, but okay, that's how I understand it. And that's why we'll maybe go faster through the section, because I don't think that's worth of time of any person. But the idea here is that if that approach worked, then we would have upper limit and lower limit, and we can say, oh, actually it's in the middle of the weak coupling and strong coupling, and some for this material it's for the That and here is another problem that weak and strong coupling predict the same transition temperature. So here this plot is also useless because we don't know what is meant. It's like a weak coupling or strong coupling. And also we have some errors which shows us that this even calculation is not it's not done precisely. So that's like really bad part of this article. Let's just read what's written here. Okay, so here it's written it's not so far from weak coupling, so weak coupling should be not so bad. That's what is meant here. And if you do these strange calculations for the strong coupling, then you will have this curve, and Macmillan says that that's a bad agreement. That's what his idea is here, what is written. Both methods predict correct in the order of magnitude. Okay. But we really... Yeah, but I don't know how to predict this transition temperature. It's just a statement. Maybe he worked with this a lot, and that's how he knows this. And now he blames mean field approximation, which is a bad thing to do because it's not clear what exactly he doesn't like in this approximation and how it can be in general improved, but okay. That's not valuable statement. That's what I wrote here. Okay, that's what I have just discussed, this plot, the idea, vertical scale, how to predict transition temperature. It's not what I know, that's already written here. And yes, I mean, that's a nice way how we can, it's actually not a line because we have logarithmic scale, but that's how we can plot the transition temperature as linear function and this squared function. Yeah, so I don't know how to obtain them, but that's what we see in this plot. Okay, finally we are reaching conclusion. That's the last half of a page. Okay, observed wave vectors may fit to geometry of electronic structure near Fermi-surface. So yes, that's what Rossnagel tried to explain, that that's a connection between these Fermi-surface vectors and the distortion vectors. And that's one idea. Another idea is the local chemical bonding. And with this bonding, maybe it's possible to check that that thing. Yeah, like local chemical bonding is just another picture, and it gives us, okay, may provide some clues so about the distortion. So maybe we can, like, I don't know what to do, because if we don't know distortion, we can't calculate chemical bonding. But okay, maybe if we, yeah, just know all orbitals, then we can find overlap integrals and check what is the most energetically favorable position, but then take into account temperature and say, oh, with finite temperature we have a different state, and if lower temperature, then we can have this distortion because of first our discovery of lower energy. That's what summarized here. Now I will just read my my comments. Yeah, we don't have working theory, so we don't know much. Yeah, it's written semi-quantitative agreement, but main message of the next sentence is that at least something is possible to do with them. It's not clear what exactly, because no explicit calculations are given and there is no appendix. It's actually a good question if there is appendix. Maybe there is this appendix which I haven't heard and thought of during all this reading and being familiar with this article. But okay, I guess that there is no appendix. And okay, that's what meant here, just like reminder of a lot of discussion which was there before. What exactly, it's not clear before and here. But still, our theories do not work well. Generic trends not correctly predicted. So again, he switches from discussion that we can do at least something or predict at least something, but it's not clear exactly what. And the second thing which he switches to is the statements about that predictions are really bad. Here, generic trends are not correctly predicted. So that's why that's typical this paper. And again, we have this repetition. Right now we have counted it's the third one, and that's just only the in scope of the fifth part. That there is not only one factor and several factors that influence, and we need to think more about it, as we have read at least 7 times during whole the stream. So let's just scroll through some of my questions which I have already asked and wrote. So that's my conclusion of the article. You already know what I think about it, that it's a useful article, and it was a great exercise for me. I learned a lot of things, but it's written like 5 times worse than I would want it to read, to be written. It's very hard to understand what is meant, and there are a lot of citations and a lot of strange statements which I consider as most likely not true statements. Like, for example, that's the biggest example. I have no idea what is meant. I mean, why at all it makes sense, and nothing is discussed here. But in general, it gave us a lot of experimental results, a lot of discussions of possible mechanisms, a lot of citations of works which were done in order to explain some of these phenomena, and a lot of precise values which can be used for other estimations. The only thing is that we need to know formulas and how to use these formulas for estimations, and that's not the case for me, and it can be the state can be achieved from this article. That's my conclusion. There are a lot of actually questions. Some of them are answered by ChatGPT, but they are rather a lot about details, so I don't think that I'm going to think really a lot of them, because in order to understand it anyway, I would need to understand the cited literature. These are just paraphrasation of what is in the article. Examples of calculations of parameters where, yeah, that thing, like some things are taken from the table, some of them are just given from the text, and we calculate this criterion. So that's a nice exercise. There could be several exercises to verify some statements. Also some questions about the background, for example, of this lattice distortion. That's what I was saying on the previous stream, that I have reached this theory why there is square root of 13 times square root of 13, but I wasn't thinking deeply about it. Maybe it's a good idea, but even better, like idea to switch article to another one, it's even better. I have some questions about details and extra properties. I have a list of questions from the stream. That's not the full list, and that's the bigger list, which I should also work out. So it will take me at least 2 hours to finalize with these questions. And let's maybe scroll. Okay, we'll not scroll through this article as I do it typically. Okay, we'll scroll maybe through this version of the article. And so that's the flashback of everything that we have done. That's 23-page article, because I exclude one page in here in the beginning of the PDF and 2 pages for the table of contents. So we have discussed everything, like introduction, that there is a charge density wave, like this unclear model. I still haven't answered this question why we have this form of distortion, but okay, that's rather technical question. This is typical plot of Pearson stability. These are the formulas that are assumed and that will be used for the evaluation of energies. Then there was the criterion, the psi and its influence in the changed phonon frequency. Then the formulas that were not used, but yeah. So if we have this, yeah, that's about this. I forgot this. So it's about this energy gap. So if it appears, then suddenly this line appears. But I need to double check it. That's how I understand it, because that's after, that's before, and we have a big spectral weight, because that's how we should understand bands. It's not one weight, it's a spectral. I mean, there could be a lot of electrons at each band. That's why we have the spectral weight. And that's actually the formula for spectral weight. And now we have these estimations for the change of the bands and some advanced theory in scope of all this approach. Advanced formulas for transition temperature, for example, for the gap. What if we change coupling from weak to strong? Oh, some theories are there, like Macmillan's theory, for example, and a lot of problems are there, and we need to take into account the electron-phonon coupling in an advanced way. What if we go to the 2 dimensions, and here we have this generalized version of electron-phonon coupling and a lot of complicated things. And what if we actually have interaction of 2 bands? Then we have excitonic insulator instability, and that's illustration of it. Nothing is clear, but there is the Hamiltonian, which is used, I guess, in some papers about excitonic insulators. And about applications to real materials, I don't remember much. We need to. Well, that's the bad part of theory, because it's not written here how we need to put the parameters of real materials to these models. Okay, then there was the third section of the just discussion of the experimental results. That's the geometry. That's some fitting to the one formula of the density of states. Some references. These are illustration of this charge density wave state. Strange plot, gap as function of transition temperature, which I don't remember much. And that's just discussion with some comments of basically this table. And what I remember is that there was a repetition of conclusion that we need to take strong coupling of electrons in order to explain some obtained results. And some comments which are not really valuable. And now discussion of ARPES results. So this about these 3 plots. And they are here, I guess, maybe with some change, I mean, with some theoretical calculations. It's not clear if they're from experimental or theoretical work, but okay, we have a lot of comments about them. Again, a lot of comments. Don't remember anything useful that I understood out of these comments. Just description of what we already see in the plots. And now it's written that this description of the tight binding model. So you need to read cited papers in order to understand what's done, but they will use tight binding models, and that's what's obtained. Like before the charge density wave gap appears, after charge density wave gap appears here, and also from here to here, but that's the bad result. So they understood, they decided to do twice distortion, which is maybe equivalent to take into account some interactions in between of the bands with this third material. And now there's discussion of this. Okay, first of all, not in scope of tight-binding models, there is the spectral weight, and that's the formula for it. It was abstract, but that's the formula that was used here in the approximation, of course, because the function is approximated by the Gaussian, as far as I remember. And if we speak about the first material, if we use the tight-binding model, then we have already seen the plot, but that's another plot which shows us the results, and they are not so far from experimental plot. That's the second material, and some comments about it, but nothing really is very important. And for third material, there is a bigger discussion because we have interaction of bands, and we have a different plot, like closed loop of that plot, which correspond to this material from that three collections of plots, which we have just seen. And some comments about the plot. And we have just went through them yesterday, but I can't recall some really important comments. Just again, repetition of abstract discussion. And now the biggest part was the biggest abstract discussion, which gives us some interesting ideas, but these are the raw ideas, so you need to read cited papers in order to understand them. So some abstract discussion, again, some abstract discussion, some, but that's about that criterion of instability, about this criterion. So, and there also those ideas, what is the driving force, what is the most important mechanism. That's rather useless discussion, but okay, we have a table which we can use for that criterion, and it was used, and it's the comments about the parameters, how they obtained, and we see that everything is approximated, but that criteria sometimes gives us transition temperatures, sometimes, I mean, at all prediction of the change density wave state. But even to reach this level of prediction, we need to know really a lot of parameters, and it's way easier to just cool system to the cold temperature and look to the STM tip to see if there is a state or not than to measure a lot of parameters and use some complicated formulas which already use big approximation. And transition temperature is the part that I propose to just forget. It's not clear what is proposed to do or what is not. It's about this plot, and the suggestion was that we need to use anyway strong coupling, but weak coupling is not that bad. But anyway, that's a very useless part of this article. And summary is the one that we have discussed during the first stream. So there is this charge density wave and periodic cluster distortion effect, and a lot of theories are there, but we have not achieved exact understanding. Yeah, so that's this article from my notes. Let's just see how many pages are there, and there are from 41 to 93, so it's a 50-page article in my like layout. Okay, finally we did it, and let's change to which this one. Yeah, I clicked the right button, so I did this challenge. I'm proud of myself. I was way more motivated to do it than without having the streams, because it takes really a lot of energy, and also if you deal with a new field, there are a lot of things that are very unclear, and this framework is very nice for just structuring the work, so I know what is the first step, what is the second step, what is the third step, and then I just forget it unless I really need some of this theory. And right now, of course, it's not clear how to use any of these theories, but I'm motivated to read some cited papers and understand better. And that's maybe what I'm going to do in the nearest several months, to read one of the cited papers from here, and maybe to understand some statements. So totally it took me really a lot of hours, basically 2 weeks of work. So thank you for your future views, and maybe tomorrow we'll do another stream, I'll see, but I'll continue doing my PhD in this direction. So that's why I'm doing the streams, not because I'm so motivated or because really these papers are so that important. I mean, that's important, 1000 citations, it's important paper, but I would choose maybe another paper if I didn't do PhD in this direction. So put like if you enjoyed the video, and bye bye.